Alright, so today we're going to be doing day 13 in Advent of Code, and we're going to be doing two different codes. One that is slower but perhaps easier to implement, and one that is extremely quick but it takes a little bit of thinking and math. So for the first part of this day, we have a bunch of text, and there's a button A, button B, and a certain price. So we imagine that this is for a claw machine, and these are the coordinates that we want to go to, and we start from 0, 0, and then we have a button that moves us in the X direction with 94 and in the Y direction with 34, and we have another button that moves us in some other direction. So what we want to do is to move some amount of A and B's. We somehow combined the right amount of A and B buttons to be able to get to exactly this coordinate. So if A was on the X coordinate 1 and then B was 10, then we could get to 100 with a lot of different combinations. But also what they want us to do is to get the cheapest one. So it says that B costs only 1 ticket to push, but A costs 3 tickets to push. So we have to find the cheapest one. And the way that we can do this is to always look for the most amount of B buttons that are possible. So look for the most amount, and then just, if it's not an exact match, the exact coordinate, then we just minus it a bit and we add some A's until we find amount that is exactly in the X and Y coordinates where we want to be. And this way we know that the first time that this will return something, we will actually have the right answer with the cheapest answer, like of how many buttons we have to push. And there's some examples here and some calculations, and then we have to return how many tokens we've used in total, so not just for one machine. So we can call this a machine. And if we go to the puzzle input, we can see that this is how it looks, and there is 320 machines if I'm not wrong. And I know that because when I was writing this, I wrote this, which says, okay, which machine it's trying, and then the amount that it currently has. But firstly, we have to parse the input data, and it's a bit messy, but we can see that after the 2 dots, there's the actual variables, and we always know that the first thing that comes is button A, and then button B, and then the result. And we see that there's always a letter and then a plus, so X and then plus, and then we have the number, and the 2 X and Y's are separated by a comma, which is useful. So the way that I've parsed it is in this while loop. So I just start from 0, and then I increase I every time I go through it. And the way that I parse it is, well, we look at we read a line, and if it starts with button A, and I want to do this just because I want to ignore the new lines, I could have just said, okay, ignore the new lines and read whatever's next, but this works as well. Then it splits it by the comma. So what it does is it splits this part by itself, so this becomes one part and this becomes another part. But we're still not done. Now what we want to do is we go to the parts. So we have the part 0 and part 1, which means the left side and the right side. And on the left side, we want to split it from wherever we find X plus. So the left side, wherever we find the X plus, will get split. So now the left side will be this, and the right side will be this, the 49. And that's exactly what we want. So I say, okay, keep the -1 space. We can also say the number 1, because the index starts at 0, so 1 would be the second one. But if we say -1, it also means to find the last one, so it's the same thing. And then I do strip, just because then we have AX as a string and AY as a string. We convert them to integers, of course, and we do the exact same thing for B and the exact same thing for the price. And we can call the price P. So I called it PX and PY. Then I append it to machines, which I've created here. It's a list, and it's gonna have the AX, AY, BX, BY, PX, PY. So the price amount that we want to get to. Then once we have all of them, I want to iterate through all of them and somehow get a cost. And to get this, I've made a solve machine function, which kind of brute forces it. So it's not the most efficient implementation, but we will get to that in part 2. So we solve this by first checking GCD, which is greatest common denominator. And what this means is if we have the number 5 and the number 10, the greatest common denominator is going to be 5, because we can multiply 5 by something to get both the 5 and the 10. So we multiply 5 by 1, we get 5. We multiply 5 by 2, we get 10. And why do we need this? Well, we want to know what the greatest common denominator of these two numbers are. And if somehow the result is not even, we can't divide the result evenly by this number, then it means that there is no solution. So if the button press in the x direction from A is 10 and from B it's 100, and the answer has to be 1002, then it's impossible to get that 2 tiny step without making this a fraction or a float. So what we want to do is to push the button entirely. We can't push it halfway or some fraction. So then we just know that it is not possible. So we just check this directly. And we check it with G1 and G2, which is the X and the Y coordinates, of course. And if this is still possible, then what we do is we iterate through B. But as I've said, it's most efficient to try to take as many B's as possible and then slowly remove them and add A's until we find a perfect fit. But we don't want to just iterate until we don't know how much. We just want to iterate through how many times B fits inside of Px. So if B of x is 10 and P of x is 100, then it's going to just fit 10 times. So we don't have to iterate more than that. And that's what I put in the range function. So it's going to iterate through this. It's going to iterate backwards. So it's going to go, if the number is 100, it's going to go -1, -1, -1. And also what this min function does, it just returns whatever is smallest. So if there's 100 here, and this is 200 somehow, but it shouldn't be possible, it's going to return the 100. But if this is smaller, if this is 10, it's going to give us the 10. And yeah, we do -1 to it, we iterate backwards. And then we want to calculate, okay, if we've traveled from the starting position of x, so that's where we want to get, if we subtract how many b's we've traveled, then we will have how many a's we have to travel in the x direction left. And we check that it is not 0 and that we can evenly divide it. So we do the modulus sign here, and we see if we can evenly divide the remaining x amount by the x from A. So if it's equal to 0, so there's no remainder, then it means that we can perfectly divide it. So then we do the same thing again, but we put it in a variable. And the reason that I said 100 here and the reason that I say 100 here is because in the question it says that, okay, we assume that they want us to press the button a maximum of 100 times. So I just check if we didn't press it more than 100 times, and if it's bigger than 0, of course. And in this case, if when we got in here, it means that every statement is true, so everything is correct until now. But we've only checked the x side, so what we do now is we check the y side with this equation. This is what we want to do. We want to get in the y direction somehow with A presses and B presses until the result. So we check this, and once we found that both the x side and the y side are true, then we have found the solution, and it is the most efficient solution. And we calculate it. So the A button costs 3 tickets and the B button costs 1 ticket. We add them together and we get the cost. So we return the cost and then we add it to the total. If it's not none, so it begins as none, and if it doesn't find an answer, then I don't even want to add. I want it to add to total cost because we can't add none. We would get an error unless we transform it, but it's just easier to do it like this. Then we just print it, and we're going to see that when I run this, it's also going to say what machine and what cost it has currently. So it took a second to start up, but now that it started up, we can see that it runs super fast. And it takes a second just because I'm printing so many things. So we can see that the numbers aren't that big, how many tickets we have to spend, because the numbers in the input aren't that big either. They're maybe up to 10,000, so it's not too bad. And we can see that every machine prints something. Not all of them have solutions, so for some of them there's just no possible way to get a solution, but for the ones that it is possible, we add them to the total, and that's this number here, 36,250. So if we go here we have 36,250, and that is correct. So now for part 2 of this challenge, we have the exact same problem, but apparently it's, I don't even know how many times bigger, a bunch of zeros. I think it's 13 zeros bigger. So what we have to do is to just assume, okay, that instead of 8,400, what we meant to read was this number in front of this 8,400. So multiply it by a really, really big number. Or not multiply it, just add it. Change where the decimal point would be. So instead of just going manually and adding a bunch of ones and zeros here, which would mean that we would have to edit the file and then save it again and then read it, what we can do is we can just directly, so we're looking at the part 2 now, and we're looking at the same function that reads it. So I'm reading it in the exact same way, and actually I'm not even changing anything, but when I'm about to use it, what I do is I just add to each px and py, I add that amount that they want us to add. So now the result is a lot bigger, and it's a lot harder to find a solution if we're making a lot of for loops to test this and that, and to slowly lower this until that increases a bit. So if we just did for loops, this would be n squared time complexity, which is horrible, and we would never get an answer. It would be impossible. And instead, what we can do is we can use a little bit of algebra. So we know that the x from the a side is multiplied by something, and then the b from the x side is multiplied by something else, and then we get the answer in the x coordinate, and the same thing in the y coordinate. And it could be that b of x is 0, and that's possible. It's just that j has to be 0, and then we only have a of x times I, which would be equal to px, so that's also possible. But what we can do is we can go from this equation here, we can multiply by bx on the top one, and by 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 on the top one, and by bx on the bottom one. And the reason that we do this is that so that we get these two things to be the exact same. So we can see that these two things are exactly the same, and since we multiplied by by on the top, then we have to add by to each term. So here's one term, so everywhere that there's a plus, it's a new term, two terms, and the third term. So we have to add ax times I, so we have ax and I, and then we add the by, which we just multiplied by. We have the bx and j, so bx and j, and then the by, and then px and by that we added. And we did the exact same thing for the bottom, but multiplied by bx instead. So we've done that. And now, since these two things are exactly the same, what we can do is we can subtract them. And the way that we subtract them is we take each term, so this is one term, and we subtract this by this, and then this by this, and then this by this. So what we get is this term over here, and then minus, so we can see it's right here, and then minus the second term on the bottom. So that's what we got. And this one over here becomes 0. So since they're the same thing, we can just imagine 10 minus 10, it's 0. 100 minus 100, it's going to be 0. So whatever it is, even if we don't know what it is, it's going to be 0. Then we do the same thing on the right side. So we take px times by minus the second thing, which is over here, and we get a formula over here. Now what we can do is we can factorize. So we can see that on this side there's i's on both terms. So we can take them outside and put inside of the parentheses whatever was left. So ax times by, and then the minus ay times bx, we put it here. And then on the right side we have done nothing. We just factorized it. Then we can put this in parentheses, which already is, and put this in parentheses, and we can divide by this entire number. So we divide on both sides by this entire thing, not by the I. We divide by this entire thing. So this means that we just put it to the other side, basically. If we divide on both sides, then this one will disappear, and this one will have the division of that number. And now that we get here, we have a single number, I, which is in terms of px, which we know, that's the x-coordinate of the prize, by, which we know, this one that we know, this one that we know, this one that we know. So all of these are just parameters from the input file. So actually, we don't have to do any for loops. We don't have to do any crazy things. We can just multiply a bunch of things together in a specific way, and then we get the answer. And to get j, we can just see that, okay, from the answer, we have gone some amount of x, so I amount, but since we know I and we know x, then we can just get to know how much is left to travel, and then the amount that is left to travel would be this, and then we divide it by bx so that we can know how many times we've traveled. So in this example here, I've made these lines to signify that, okay, we've done it 3 times. So this is essentially what we're doing. Where we have a starting position, which is 0, 0. We're trying to get to px, py at this point over here, and then we can travel. If a is in this direction and b is in that direction, we have to combine some amount of a's and b's to get there. So the a would bring us over here, and then the b would bring us over there. That's what we're trying to do. And we can go with the b first, so we can go upwards first and then right, or we can go just 1 step in the a direction and then 1 step in b, another step in a, and then 2 more in b. It still brings us to the same place. So now that we have this equation right here, which is what is going to help us, we can implement it in Python. So I've added the numbers to px and py because that's what we're supposed to be working with, and then I've made the variable denominator, which means the thing that it's divided by. So we can see it's divided by ax times by minus ay times bx, ax times by minus ay times bx, and we have to check if it's not if the denominator is not 0. If it is, then we're gonna get a problem because we can't divide by 0. So we have to check if it's not 0. We don't actually have to. I've tested it without it, and at least with my input file it works just fine, but it's good to never divide by 0, even if you know that it's not gonna happen. So now what we want to do is to get j instead. So we have I by doing whatever was on the top side divided by the bottom side. So this is on the top side divided by the bottom side. We get I. That's exactly what we're doing. And then we have this thing here, which is the exact same thing that I wrote here. And then we divide it by bx. We divide it by bx. And since it's another division, we have to make sure that bx is not 0. So it's another prevention to not get an error. And now that we have these i's and j's, what we can check is, okay, are they whole numbers? And we can do that by saying percentage, which means modulus. So if we modulus it by 1, then is there any remainder? So we can do this a number of ways. We can just check if the variable type is an integer or a float, but in Python it casts it automatically, so we would have to make some more code. It's just simpler to do it like this. So if there is no remainder for I or j, and if they are bigger than 0, because we don't want to get some weird answer where it says, okay, press the button -5 times. We can't really do that. It has to be positive. Then we just calculate the total cost. So it's 3 for the A buttons that we press, and then 1 for the B buttons that we press. And that is how many times we've pressed them. Then we return the cost, and I've done the exact same thing here. I added to the total, and I also have trying machine and how much cost. So if we run this, we will get a bigger number, a lot bigger, but we can also see what number each machine returns. So if we go to the website, we can see that it's 832 and it ends in 012. 832 and it ends in 012. So that is also the correct answer. So this was a lot faster, but now to talk about the time complexity of part 1, it's slower than part 2 actually, just because of how we implemented it. So it's the time complexity is n times b max, and b max is however much px divided by bx is. So how many times bx fits inside px, and divided twice, this means to get how many times it fits inside. And since in the worst case it's going to be 100, then it's just 100n, which means it's O of n. So it's not too bad, but it's only because in the question they specifically said, okay, we can assume that it's less than 100. So technically still constant time. And then the space complexity is O of n to just store all the variables. But in part 2, the time complexity is a lot better, because if we look, we don't have any for loops at all. We just have an if statement here, an if statement here, and that's it. The only for loop that we have is when we iterate through all the machines, which we have to do to check all the machines. So this is extremely fast, and it's just O of n. And n is not even all of the lines, it's the number of machines. And we can see that for each 4 lines we have 1 machine, and we had let's see, 1,200 something lines. And if we run this again, we can see how many machines there were, 319, but it starts from 0, so it's 320 machines. So it's a lot faster than the first implementation, and we can use this code for the first part as well. We can just remove this, and it should work exactly the same. So we've done that, we run this, and I hope it doesn't break. There we go, 36250. Now if we run the first one, do we also get the same number? 36250. So it's the exact same code essentially, just a different implementation. So that was the time complexity for both of them. This one was constant time, which is amazing. And now for the leaderboard, if you guys want to join, I will leave the private leaderboard code in the description. And there's a couple more people that have joined, which is great to see. And yeah, thank you for watching. Happy holidays, and see you tomorrow.